All right. So for our project, we did a self-tuning guitar. And just a quick overview, we'll start with some of the background on what exists out there already as far as guitar tuning. And we'll go through an overview of the design, block diagram of our circuitry, then in some more detail on each of the components. Thank you. And flow of how the software component of our project works, and finally go through a quick demo. So the background, most tuners right now that are fairly cheap are going to give you some visual feedback. You pluck a string, you see whether you're sharp or flat. The few automated solutions that are around are very expensive. I believe there's one guitar for around $2,500. Which is not nearly what we spent on this project. So what we wanted to do is get some kind of cost-effective, ideally a retrofit to existing guitars, and get the tuning done with minimal user intervention. So here's what we're doing. We have the 6 guitar strings. We're using piezoelectric pickups on the guitar. So this gets bumped up to our 2.5 volt level. This gets buffered into a set of filters so we can kind of bandpass each of the strings, and then we detect the frequency using the Arduino, and ultimately we tune the guitar using the motors.
Thank you. So this is just a picture of the circuitry we have. We designed and had fabricated a PC board for the filters, and actually we were going to use an Arduino Nano. Had it working with this, and yesterday this burnt out. So what you see here is our attempt to retrofit another Arduino to get everything running. So yeah, these are just the filters, and okay, so this is the signal we're getting from the piezo pickups when you plug a string. After going through our bank of through our bandpass filters and amplifying it, we got something like this, which we passed into the Arduino, and then used zero crossings to find the frequency for that string. And this is just kind of a picture of the filter we use, second order bandpass filter, and this is just a simulation of each of the 6 strings being filtered.
So the Arduino accepts 6 analog inputs, and then using the analog read call, we read the analog input, and from there we detect the frequency of each string, as Alon said, using zero crossing method. And from there we use the Servo library, which Albert will talk more about when he discusses the software, to control the servos and tune the strings. For the motors, we chose parallax continuous rotation servos, and we chose them because we found that they have enough torque, which was about 60 ounce-inches, and which is far more than enough to turn the pegs. And they're also very cost-effective. They're about $15 each, and they're more or less the cheapest ones that we could find, which more or less the cheapest continuous rotation servos that we could find. And to mount the servos, this is actually something that we couldn't have done without a couple of friends in the mechanical engineering department. And they helped us with the laser cutter and came up with a very elegant solution. As you can see, we used shaft couplers to mount the servos to the tuning pegs. And we disconnected the tuning pegs and used shaft couplers to connect to the shaft. And then this acrylic mount was cut from using a laser cutter. And basically, it's just using double-sided sticky tape is attached to the head and prevents the servos from moving at all while they're tuning the guitar.
So I'll talk a little bit about the code that's making this run. So we've got this constantly looping thing that will start with a button press. So once the code is running, this is the on-off switch for the Arduino. This will give the whole tuning stage power. So we can turn it on, nothing will happen. Pressing this button will engage the tuning mode. So we've got 3 LEDs to indicate which string is being tuned. Currently, we're only tuning one string due to a variety of problems. One of the channels on our piezo bridge burnt out yesterday, Then we broke 3 strings, and now we're down to 1 string. But anyways, so we wait for the button to be pressed. Then it starts cycling through each string, waiting to tune each one, using this LED to tell the user which string is being tuned. We had to make a few modifications to the Arduino code to get this to work. One of the problems we ran into at first was that the analog read only reads at 10 kilohertz, and this would be like below the sampling frequency we needed to get something accurate. So something pretty easy that we did was we changed the prescale factor in the Arduino. Basically, this changes the resolution at which analog read reads. So we just changed that from 128 to 16, so we only have 16 steps of resolution. That's all we really need because we're doing zero crossings, and we get like 77 kilohertz of sampling rate, so it's like fine for our channels. So after that, our code detects a certain threshold for each string. So once the amplitude of the string is above a threshold, meaning that it's plucked, it will start the frequency detection. After the frequency detection, we have some like software low pass filters that will filter out like crazy results. Because if you like pluck the string a few times quickly, then you'll introduce new frequencies into the string. So we use that sort of like first order, first pass filter, low pass filter to filter out those kind of frequencies, and some just stray frequencies that it seems to read every once in a while, because we don't want the servos going crazy. Then we used a very simple algorithm to control the servos. At first, we wanted to use a PID algorithm, but as it turns out, we don't really have the degree of control over the servos that's necessary to use a PID algorithm. We found that below a certain threshold of values outputted to the servo, it just wouldn't turn. And this was due to the fact that there's like a pretty nonlinear torque distribution in these pegs. Like turning each peg, first of all, will have a different torque. Secondly, at different points in the rotation of different torque based